the titration of a strong acid with a strong base. That's one type of titration, or a strong base with a strong acid. And then we have a weak acid titrated with a strong base, or a weak base titrated with a strong acid. So while they're doing the same thing, allowing us to quantify amounts of acids and bases, the math manipulations that we need to do and the chemistry that we're looking at is slightly different in either of these cases. So we're going to treat them differently, but I'll talk about both or all three of these types. And so what we're going to do, and what you've probably done before, is made a plot, a titration curve with pH on your y-axis and the volume of titrant on the x-axis. And so you may remember seeing something like this. Okay. So we're going to basically go through each part of the titration curve, think about what's happening in solution, and talk about how to calculate pH at those points. All right, so here we have, we're going to start with the titration of a strong acid with a strong base. And so we have a couple terms to learn here. Titrant, that is what goes in the burette. And the titrand, with the D, that's what's in the Erlenmeyer flask or in the beaker or whatever. So when we titrate a strong acid with a strong base, we're going to put our strong acid in the flask. That's what I have here, HCl. And we have our base in the burette, okay, sodium hydroxide, and that's what I have in the burette here as well. Now, when you think about what's in solution, we know that HCl is a strong acid, forms H plus and Cl minus. And so for sodium hydroxide, completely dissociates to form sodium ion and hydroxide ion. And so when we combine these solutions in small quantities using our burette, we are taking advantage of the neutralization reaction. Okay, so we'll have H plus plus OH minus giving H2O. And this single arrow occurs to completion. Okay? Everyone okay so far? Sometimes you also can measure the pH of the solution. We're going to talk about how to calculate that. I didn't bring a pH meter today, but I might on Friday. All right. Okay. So again, this is a general titration curve for the titration of a strong acid with a strong base. Notice that our pH starts off low and then ends high. So that's how you know you're starting with an acid. Okay, when there's zero added base, that's on our x-axis, we have a low pH. So this first point, the only things that are in solution, so this is before any base is added. So before OH minus is added, the only thing that we're really worried about affecting the pH is H plus. Okay, that makes sense. Only HCl in the flask, so pH is dependent on the concentration of H plus. Then we start adding some hydroxide. Okay, so we have here 0.2. You can notice that the pH is increasing slightly. All right. Here we have, so this is when we add some OH minus. And the pH is going to be dependent on the amount of H plus that's left after reaction with the added OH minus. So the calculation there is still going to be whatever minus the log of H plus, but you have to figure out how much H plus is in the solution. Right? Point 3, this is the equivalence point. So the equivalence point is defined as the volume. I'm going to abbreviate equivalence point as EQPT. This is when the moles of hydroxide added equals the moles of H plus initially. So that's the definition of the equivalence point. Okay. I want to point out something about this. There's another important point along the titration curve that we're going to see when we have a weak acid, and that's halfway to the equivalence point. For a weak acid titration, halfway to the equivalence point, you have equal moles of weak acid and base in solution. Okay? Here, we've completely reacted at the equivalence point. This is true in a strong acid, strong base, weak acid, strong base titration. At the equivalence point, we've completely reacted all of that acid away, and now we're left with, in a weak acid, base in solution, or here, we're left with just water. Okay? So point 3 is the equivalence point. And so the pH is dependent on the equilibrium of water reacting with itself, the Kw. Whoop. Okay, so in a titration with a strong acid titrated with a strong base at 25 degrees Celsius, the pH at the equivalence point is equal to 7. We've completely reacted away any acid with the base. No excess of anything. The only thing left in solution is water, plus some salts, Cl minus and A plus. But as we know, those don't affect pH, right? So then, at any point past the equivalence point, we have excess hydroxide in solution. And so the pH is dependent on the concentration of OH minus. If we know the concentration of OH minus, we take minus the log, find the POH, and then calculate pH from there. Yes?
Can you go through every step and show which ions are present?
Sure. Do I do that? We're going to go through each step, so let's do a calculation for that so we can talk about what all is present there when we do that. Does that work?
Sure.
Okay. Okay, any other questions? Okay, now on our titration curve, what our calculated pHs were. So our initial pH was 1, and that looks like it's going to match up pretty well here with our titration curve. That's about 1. Then we calculate, I could see that being real. Sorry I covered up the thing there. And then at point 3, our equivalence point, that's going to be pH of 7. And then past the equivalence point, looks like we're, depending on where we are, above 12. So we've calculated 12.2, something. So it matches up with our calorie. So let's say we have 25 milliliters of 0.1 molar HCl. A little different than what I actually have in the flask, but that's okay. And we're going to titrate with 0.1 molar sodium hydroxide. We're going to calculate the pH at the 4 points that we discussed, the pH before any base is added, pH when 10 mils of sodium hydroxide have been added, pH at the equivalence point, and the pH 10 mils past the equivalence point. This is a summary of what we just talked about on the previous slide. Just to put at point 2 with our Okay, so let's start with number 1, pH before any base is added. Okay, so again, in our flask, so we're going to be thinking just about the ions that are present in the flask. We're going to have H plus and Cl minus. Okay, we haven't had any sodium hydroxide yet. And so in order to calculate the pH, we just need to know the H plus concentration. And given in the problem, it says that we have 0.1 molar HCl. And so we can find the pH. pH equals minus the log of 0.1. And we'll end up with pH of 1. Okay, make sense? That one's easy. Okay, now let's start doing some chemistry. Degree 7 titration. So in the flask, we're going to have our H plus and our Cl minus from the hydrochloric acid. And we're going to add 10 mils of sodium hydroxide. So when we add those ions, we're going to add Na plus and OH minus. Okay. The sodium and the chloride are going to act as spectator ions. Okay. And so we're going to see that we're going to do the neutralization reaction. H plus plus OH minus. It's going to yield water. Oops. Okay. Because we're looking at a reaction, we need to use a reaction table. And in our reaction table, we need to have moles, not concentration. Okay, so we need moles of H plus and OH minus. So we'll take the volume of the HCl, multiply it by the molarity. So we'll have 0.025 times 0.1, and that gives us 0.0025 moles of H plus. For the hydroxide, we've added 10 mils of the 0.1 molar hydroxide. So 0.1 molar times 0.01 is going to give us 0.001 moles. And of course, we don't worry about water. And so now we have a limiting reagent problem. Here, the hydroxide is the limiting reagent. And we know that to be true simply from our titration curve. We are before the equivalence point. Okay? So if we're before the equivalence point, our hydroxide is always going to be less than the hydronium ion concentration. I definitely got soap under my watch. That is itchy. Okay, so we're going to do minus 0.001. And we'll be left with 0.0015 moles of H plus and 0 moles of hydroxide. Okay. So then we need to calculate the concentration of H plus. We know our moles. We need to know the total volume. And the total volume is going to be what we started with, the 25 mils plus the 10 mils of hydroxide. So we'll have 0.035 liters. and we will end up with 0.043 moles per liter. And we can plug that into our equation for pH, minus the log 0.043. And we get 1.368. Questions on that? So the pH has increased, but not drastically. And that's because there's so much excess H plus in solution. So in our demonstration here, we're going to do a titration with the phenolphthalein indicator. So right now we have a colorless solution. At the equivalence point, it'll turn pink. And so our equivalence point should occur in this setup at about 10 mils of base added. So we're at about 9 right now. So I'm just going to add, say, 5 mils. This is, oh gosh, okay, stop being anal, all right. Oh. All right, so you can see some pink color. That's the indicator. As I stir, that goes away. All right, so here we're still past the equivalence, or excuse me, before the equivalence point. All right, so there's that, okay? That's where we are here, what we're talking about with our titration. Okay, to our previous problem, we know that we're starting with 0.0025 moles of H plus. I get 1 point, I don't know why I keep. So then let's calculate what the pH will be at the equivalence point. This should be an automatic one. I'm going to show you just why this is, basically restate the definition. But one of the things that we don't know with this problem is the volume of base that's required to get to the equivalence point. If we go back, okay, so in solution we're going to have our H plus, we're going to have Cl minus, sodium, and hydroxide. The initial moles of H plus in these reaction tables is always going to be the same. And at the equivalence point, the definition is that we've added the same number of moles of hydroxide as we initially have of H plus. So we're going to have 0.0025 moles of hydroxide. And in this case, we have equal moles of everything. So after we react, we're left with 0 OH minus and H plus. And so the pH is dependent on the equilibrium for water. Sometimes you'll be asked to find the volume at the equivalence point. Okay. And if you're working on homework problems and it asks you to find the pH at several different volumes, but it doesn't explicitly tell you that one of them is the equivalence point, it's a good idea to first check the volume at which the equivalence point occurs, because then that'll help you figure out where you are on the titration curve for those other volumes. So in order to do that, we need to find the volume of hydroxide that's required to get 0.0025 moles. Okay, does that make sense to everyone? And so we'll multiply or divide, by our molarity for sodium hydroxide. is 0.1 moles of OH minus per liter. And so we'll end up with a volume of 0.025 liters or 25 milliliters. Okay. Everyone okay with that calculation? So let's reach the equivalence point for our titration. Let's see how good I am today. I'm getting close, I can tell. So with an indicator, it's not a perfect calculation and determination of the equivalence point. It's actually referred to as the endpoint, just slightly different terminology to represent the fact that you're using an indicator. An indicator will change color in a range of pHs. There's a lot in your textbook about it, a good amount, but we're not going to spend a lot of time on that in lecture. So you notice the pink is sticking around a little bit longer, so that means I'm getting really close. There we go. All right. Going away slightly. Probably half drop more. There, that'll do it. Okay, so that represents our endpoint, which in this case we're going to call the equivalence point. And that should have a pH of 7. I wish I brought my pH meter. All right. Just said that the equivalence point, go back and calculate. So then if we go past the equivalence point, all right, this is a pretty dark pink color, but this should get more pink as you add more base. Yeah, that's getting there. That is a strong indicator they put in there. Whew. Okay. So now what we have in solution, past the equivalence point, we still have sodium ion, we have hydroxide ion, and that's what our pH is dependent on. We also still have chloride ion. But we've reacted away all of our H+. Okay? Now you might say, isn't there H+ because we have water and it has an equilibrium? Yes, but it is very, very small because the hydroxide is so concentrated. It's going to push that equilibrium back to the right, to the reactant side. So 10 milliliters past the equivalence point occurs at 25 milliliters. So we'll do our reaction table again. Again, starting with the 0.0025 moles of H+. Now we've added a total of 35 milliliters of hydroxide. So we need to find the moles associated with that. It's going to be our 0.1 moles per liter times the 0.035 liters. And so we'll have 0.0035 moles of OH minus added. Okay. Again, we have a limiting reagent problem. This time, H+ is the limiting reagent. minus 0.00250. And we're left with 0.0010 moles of OH minus. So at this point, we need to find the concentration of OH minus. So what's our total volume? Yeah, 60 milliliters. So we've added 35 with the base, and we started with 25 of the acid. So we have a total of 60 milliliters. So our hydroxide ion concentration is 0.0167 molar. POH is going to be minus the log of that. And I get 1.77. So the pH is going to be 14 minus 1.77, and that's 12.22. Make sense? Yeah.
Can you say again where you got the
Yeah, so the total volume is going to be the initial volume of HCl, 25 milliliters of that solution, plus what it took to get to the equivalence point, which was the 25 milliliters. And then in this step, we're saying we're going 10 milliliters past that. So we're going 0.035 liters from the addition of OH minus. Okay. Cool. What else?
Why did you use that 0.0025 moles of H plus if there's none anymore?
So in the reaction table?
Yeah.
Okay, that's a good question. So I know we've done this problem stepwise. So we said we got to the equivalence point, and then there's no H plus left in solution. When you approach these problems, kind of forget about that, okay? And assume that the reaction is starting from 0. Picture in your mind that you're going straight to 10 milliliters past the equivalence point. So you're reacting HCl with 35 milliliters of the hydroxide, okay? And so, yes, all of that H plus goes away, and now you have excess OH minus. There are other ways to get to this calculation as well. And if you find a different way and you like it and it works, that's fine. Okay? Yeah, I'll leave it at that. Other questions? Okay. Sorry. Okay. So with a weak acid, it's the same sort of ideas. Now you just have a little bit more complication because we have to deal with both a weak acid and its conjugate base that's produced in the reaction. So I really like this plot because it shows the difference in what you would expect for a titration curve if you're using a strong acid, which is the dotted line now, versus that for a weak acid. And on here, slide 36, so for the weak acid, you'll notice that the starting pH is higher than that for the strong acid. So looks like we're around 3 or above for our weak acid, and we were at 1 for our strong acid. The other really big clue that we're working with a weak acid is where the equivalence point occurs. And that is going to be at a pH greater than 7. Okay. And that, why is that? Let's start with why is that? So when we have our weak acid, we'll just call it HA, and we react it with OH minus in this titration. We're going to form A minus and H2O. Okay. But what does A minus do in solution? It's going to be in equilibrium with the weak acid and OH minus. And so this OH minus is going to tell you that the pH has to be above 7. You're going to have some amount of hydroxide in the solution at the equivalence point. At the equivalence point, this reaction has occurred to completion, and now we have this equilibrium in play. Okay. Another cool thing, though, is that the volume at the equivalence point is the same. Why is that? So it's the same for a weak acid titration or a strong acid titration. And that's based on stoichiometry. One molecule of weak acid is going to react with one hydroxide ion to form products. One strong acid ion is going to react with one hydroxide ion to form products.
So in the last question, we had a weak acid, so strong acid, it would still be the same volume?
Yeah.
Okay.
So if last problem we did, well, instead of a HCl, we had a weak acid, the volume at the equivalence point would still be the same thing, 25 mils. Okay. On the previous slide, that all of the HA is going to react with the hydroxide, completely reacting away HA, to be left with. So we can go through again and look at what's in solution at each of these points along the titration curve. So at point 1, this is before any base is added, just as it was before. And now what we have in solution is our weak acid, and it's in equilibrium with its conjugate base. Okay, we've got our H3O plus in solution now, so we know that we're going to have a acidic pH, less than 7. Hang on one sec. I hope it works this time. I don't know how they do this. All right. Okay. So at point 2, now we've added some amount of hydroxide. Very slippery. Which means that some of the HA has reacted with the OH minus to form A minus and H2O. But not all of it, okay? So it's before the equivalence point. So in solution, we're going to have HA and A minus plus whatever salts. Maybe a Cl minus. Probably not a Cl minus. Excuse me. The salt from the hydroxide, Na plus, something like that. Hey Ryan, since I can see you, would you like to be a bubble piler today? And if someone else has any other ideas on how this is done. They just told me to keep piling it on top. Here's the instructions if you'd like. Hey now. All right. So what do we have when we have HA and A minus in solution? Weak acid and conjugate base makes a buffer. But that's not actually so bad because we can use our Henderson-Hasselbalch in that region, right? Okay, so at the equivalence point, I just showed minus. So we're going to have A minus in equilibrium with HA and OH minus. Okay, so I know this is not a buffer, okay? We do have A minus and HA in solution, but that's only after the equilibrium has happened, okay? So what we're concerned about is an initial concentration of A minus, and that reacting to form HA. Okay. Does that make sense? So this becomes a weak base problem.
So it's not a buffer at 3, but it is at 2.
It is not a buffer at 3, but it is at 2. And at 3, it's a weak base problem. With an ice table, KB value, that kind of thing. That's looking much better. Okay, then past the equivalence point, we're adding excess hydroxide. And so the pH again is going to be dependent on the amount of excess hydroxide. Okay. It's gross, right? Okay, 2 slides.
Oh, I just need to put a tray to send it back.
Oh, okay. Any questions? All right. Let's light this thing one more time. Maybe it'll be better. Do you want goggles? There are. That's better. Thank you. I just didn't wait long enough the first time. It seems like there was just extra ventilation. My hands are very cold now. If you're not part of the reflection, that's not. Or do you have one? You're taking our picture.
I mean, is there grade?
I have no.
Okay, I thought they said, I know you said there might be a financial one, but I didn't know that.
Financial now.
Like $5.
The email.
Okay.
I went to Dr. Moore. She I think she sent an email to everybody.
Yeah, I had no
basically
idea.
grade LCP quiz or attempt 1. I come back, I went and talked to her. I told her basically what came up with it. She was like,
Holly might help.
I know that's
we'll just have them
Yeah.
review it.
So during the test, I asked one of the TAs just about, because all the answers, they said like 4.01 times 103, or like something like that, not 10 raised to the third power. So I don't know who I would talk to about that, because like,
3 minutes left. So while we're waiting for a few more bubbles, let's just finish off the step 1 here. This one's the drama bill. Easy. So let's take a 25 milliliters of 0.1 molar formic acid, put that in a flask, and titrate with 0.1 molar hydroxide. And we're given a Ka for this, 1.8 times 10 to the minus 4. Okay, so the first thing is, what is the pH before any base is added? So I'm going to abbreviate formic acid, HA. So in solution, we only need to worry about the equilibrium with the weak acid, HA plus H2O, in equilibrium with A minus and H3O plus. Okay. I'm going to skip the full ice table and just give you the equilibrium line. Everyone okay with that? You all are experts now. Okay, so we're going to start with 0.1 molar formic acid. I'm not going to worry about water. We're going to form some of that formic acid minus X is going to react, and we're going to form X amount of A minus and X amount of H3O plus. And so we can use our Ka, 1.8 times 10 to the minus 4. Set up our equilibrium constant expression, 0.1 minus X. This one, if you check your assumption, you'll find that it's not valid. So you should use the quadratic. But this should be all old hat right now. So, okay, we can't ignore X. We have to leave that there. When we multiply this out, I'll just write my quadratic equation here for you. 1.8 times 10 to the minus 5 minus 1.8 times 10 to the minus 4x minus x squared equals 0. Solving for x, you'll get 4.2 times 10 to the minus 3. And this is equal to the concentration of H3O plus, as you can see from our ice table. So pH minus the log of that, 4.2 times 10 to the minus 3, we should get 2.38. If we remember back to the very first problem with the HCl, initially that pH was 1, here we're at 2.4, that makes more sense for a weak acid, right? Less acidic. Yeah, I'm kind of disappointed. Let's set it on fire. Do you want to do it since you've been in helping? Sure. Okay. Let's turn off the gas. What's that? What's that? Oh yeah, the hose. Yeah, it actually goes into his water.
Before you do that,
Side.
can you go back 2 slides?
Yes, we have a question.